Alrighty. So, folks, remember, if you're not interested in this problem, just do other work. We kind of try to be a little quiet about it, especially if you're sitting in the front. Just because, So we got this bicyclist who rides a bike and has a certain speed, and we're asked to find out the work done on the brakes to bring the rider to a stop. So, looking at my bar graph, I'm going to say that the rider had a lot of kinetic energy to start. Pick a better color. And then at the end, the rider is completely stopped. They don't say he goes up a hill or she goes up a hill or anything. So I'm going to assume that there's no other energies going on. So all the work external goes to taking away that kinetic energy through work done. Usually it's brakes or, if your brakes fail, how do you stop on your bike? You put your feet down. You rub your feet along the ground. And you're doing work on the ground through that frictional force. So there's my why. All that kinetic energy it has, the bike and the rider have at the beginning have to be removed by negative external work. Good? Alright. Excellent. Let's grab some equations that we'll need. I think we'll need our equation for kinetic energy. We'll probably need our work equation. From our equation sheet. Or your mind if you've memorized them. So, let's do part A. In part A, how much work is done by the brakes to bring the bike and the rider to a stop? So from my Y, I know that whatever kinetic energy has at the beginning has to equal the work external. Done on it, right? They're the same magnitude, just different. One is the external work we said is negative because it's taking energy out of the system. But here we're just comparing their magnitudes to each other, how big they are, since we don't have a directionality, and we wouldn't use one. Alright, so I've got the mass. Now be careful, the mass is the mass of the bicyclist and the bike, right? And so I'm just putting in here, this would be 1/2. The mass of the bicyclist and the bike for me is 77.8. And then the speed squared, and that is my answer. Questions? Excellent. On to part B. What is the magnitude of the braking force? So, I have my answer from previous. F is what I'm looking for. For me, they tell me my braking distance is 4.0 meters. All for F. From my problem, it told me that I'm trying to think of the wording. If the bicycles come to rest in 4.0 meters. Yeah. Yeah, because I did Part A in blue, part B is in green. Yeah?
Wait, how do you solve part A? What do you do after you have that?
Arithmetic. All right, so we have an apple falling from a tree from a certain height. We're asked what is the kinetic energy, potential energy grab, and total system energy at some height below that, but not at the ground. And we have no air resistance, so we have all conservative forces. So I'm going to go in here and give myself a PE grab column. Good. And when I'm going to go from, my initial is going to be when it's at that 4 meters above the tree. When it's at 4 meters above the ground. And then my final is going to be looking at it at that second height. Is how I'm thinking of it. So at my initial height, all I have is PE grab. When it's at my lower height, it's going to have less PE grab. And that PE grab that went away went into kinetic energy, or became kinetic energy as itself, and no external work. So that's my Y for 5. Do you match up with your Y? Okay. Almost. All right. So. So I'm going to say PEG at 4 meters. I think mine goes from 4 meters down to 3 meters. Right, yep, 3 meters. Equals PE grab at 3 meters plus KE at 3 meters. So my totals, and both sides of this, I could say equal my total system energy. Because that's all the energy that's going on here. It's all that mechanical energy. And there's no non-conservative force, no air resistance, no outside work being done, so that mechanical energy stays conserved the whole time. So I forget which part is, oh, I want to find all 3. So, I might do my energy total, and that would be mgh at 4. I might figure out that number first, and then I know that number equals PE at 3 and KE at 3. I could find the PE at 3, right? That's just mgh at 3. I could use those 2 answers to find my kinetic energy at 3. It's how I'm going to approach it. because this, of course, is this answer. This, of course, is this answer. If A equals B plus B, and I know A and B, I can find C. One of those algebraic things. Yeah, I think they want them separated by a comma. So put in your kinetic energy, comma, your potential energy is 3, comma, your total energy. All in joules. Sure. So that's where I got that equation from, that green one, right? And that's why I find these Y's so helpful. It shows me how to set up my major relationship. I'm going to give it a try. You should give it a try. Yes, sir. So here's my Y for 6. Where we have the ball. The ball, when it starts off, I said that at the point of release, the gravitational potential energy is going to be 0. And therefore, as it rises up, that PE grav will increase. But to have energy to increase the PE grav, it's got to take it away from the kinetic energy, so it's going to slow down. All right? So, actually, why don't we just go back to where I did it? I know, I'll do it.
To find tools that are, and then like divide them into energy by the graph.
Right? What did 6 actually ask for? Oh, the height. The height. Okay. Well, as I wrote, it's KE at the release. It's going to equal its KE at the top plus its PE grav at the top. And now I'm substituting in 1/2 m v at speed at release, 1/2 m speed at the top, which is what I believe I'm looking for. M G. Oh no, I'm looking for H, right? So I know everything. Can I simplify that algebraically at all? I can take out the math. Now, basically, it's algebra. It starts fitting in what I know. So you get H. Yeah, you could take out all the masses because they're in every term. One of those cool algebra tricks. If there's the same term in same variable in every term, it disappears.